Good morning to all. I am Dr. Alna Priyadarshini. In today's class, we shall discuss about the effects of rain. So, in C band as well as Q band, the effects of rain will has a significant effect. So, it results the rainfall, which results in attenuation of radio waves by scattering and by absorption of energy from the wave. Rain attenuation, which increases with increase in frequency, and it has severe effects in the signals which are transmitted in Q band as well as in C band. So uplink rainfall margin. So rainfall results in the effects of this rainfall that has severe impact on attenuation of the signal, increase in noise temperature, and all these degrades the carrier to noise ratio of the signal. So some form of the uplink power control is necessary to compensate for rain fades. So as the from compared with the frequency, as the frequency increases, the during if the high frequency signals are transmitted due to the effects of rain as well as the water drops and the moisture content presence in the atmosphere, that will increase the absorption loss. So because of that, the signal is get scattered a lot, and the signal quality of the signal is get degraded very highly. So in case of the uplink power control mechanisms are highly recommended to provide compensation for the rain fades. The power output from the satellite may be monitored by a central control station, or in some cases, the output power from the satellite is monitored by the earth station in the various locations. The power output from any given earth station can be increased if they require to compensate for fading. So the earth station in the earth station, high power amplifier are used, so they have sufficient reserve power to meet the fade margin requirements. For example, in Ottawa, there's a earth station is there. So here the rain attenuation which exceeds a range of 1.9 dB for 0.1% of time. So this means that it is to meet the specified power requirements at the input of the satellite for around nearly 100% of time. That is approximately, that is exactly 99.9% of the time. The station must be capable of providing 1.9 dB margin over the clear sky condition. So next is the downlink rain fade margin. So this downlink rain fade margin that is and that discussed about the signal that are received from the satellite. So from satellite to the earth station, the signal will be transmitted in the um, uh, 10 power 9 hertz range of frequencies. So that's a very high frequency, and the signals also get absorbed as well as scattered due to the effects of rain as well as the moisture content in the raindrops. So here also the rainfalls which introduces attenuation by the absorption and scattering of signal energy, and the observatory attenuation introduces the large amount of noise. So because of that, the quality of reception is get degraded, and we cannot receive the high quality signal. That means the signal strength is get completely below the required level, so that we cannot receive the signal as such. So the here let us consider the effects of this rain is discussed. So in the downlink case, so let us consider a dB, which represents the rain attenuation caused by the absorption of the signal, and the corresponding power loss ratio is given as A, for A is equal to 10 A by 10. Therefore, the effective noise temperature of the rain is calculated as T rain, which is equal to T naught into 1 minus A by 1 minus 1 by A, where TA is known as the apparent absorber temperature. So it is a measured parameter which is a function of many factors, including the physical temperature of the rain and the scattering effects of rain cell and the thermal noise incident upon it. So the value of the apparent absorber temperature lies between 270 and 290 degree Kelvin. So with the measured values of for North America lying close to just below the freezing of 273 Kelvin. For example, the measured value given by Weber is in this paper, they have obtained the values as 272 so Kelvin. The total sky noise temperature is the clear sky temperature plus the rain temperature, which is given as clear sky temperature plus rain temperature. So therefore, the rainfall degrades the received signal to noise ratio in two ways, by alternating the carrier wave and by increasing the sky noise temperature. Thank you.